Welcome back to the Amateur Radio Online Technician Licensing course. This is session 2A. The session has actually two videos attached to it. We'll be doing all of both session 2A and 2B in the same night, but for the sake of the size of the recording, I decided to break it down into two pieces. So let's begin with AC and DC electricity. Now, before we get too deep into this, I just want to remind you that we're going to go deeper into the material than the book does. And again, the reason for this is just to give you a little bit better foundation for the technology involved in amateur radio to help you as you progress later in the hobby. However, the only thing you're actually responsible for the licensing exam is what's in the book and reflected in the question pool. So keep that in mind. I'm going to go a little bit deeper than you would if you just went through the book itself. So let's start with how you generate electricity. So the first method we're going to talk about is induction, which is moving a wire through a magnetic field or vice versa, that is moving a magnet through a set of coils or wires. And this pushes electrons in the wire and creates a current. So you can see on the right, we have a magnet that's going through a coil and it's deflecting the voltmeter to the right, which is a positive voltage. And then when the magnet is moved out, it's deflecting the meter to the left, which is creating a negative voltage. This is an alternating voltage or an alternating current. This is the basic idea behind power generation in power plants like coal burning power plants, oil burning power plants, and gas burning power plants, and nuclear power plants as well. So any of those all have a generator somewhere in the system to generate electricity, and this is basically how they do it, or how it's done. The second method is through chemical reaction, and we're talking here about batteries and fuel cells. And what they do is chemically create an excess of electrons that can be used by a circuit. And the third one is a photoelectric effect, or photovoltaic solar cells. And they use light energy to free electrons from semiconductors, which then makes them available to do work, that is a current that can be used by a circuit. So those are the basic three methods: induction, chemical reaction, and photoelectric effect for producing electricity. And there are two types of electricity that we deal with in amateur radio. The first is called direct current, which is basically a battery or alternating current that's been converted into direct current. And that is, we have one voltage, and that voltage stays the same throughout the time that we're going to be using it. Now, if you have a battery, batteries will lose their voltage over time, and so they will become depleted, and you'll see they have a discharge curve that over time will then bring them towards a voltage of zero or a cutoff voltage of some sort, but they will be depleting their voltage, and so therefore the direct current only lasts for a specific period of time. And on the right we see alternating current. And alternating current, the US standard is 60 hertz or 60 cycles per second. And the peak, that is the voltage from 0 to the highest positive, is this 170 volts. We'll find out later that we call that 120 volts because that is the DC equivalent value. When we calculate it as a DC equivalent value, it's 120 volts in the line socket. But its peak is 170 volts positive. So those are the difference between direct current and alternating current. Almost basically every piece of amateur radio gear uses direct current. And so we may have a power supply associated with that piece of equipment that's going to convert the alternating current into direct current so the transceiver can operate. The reason that they operate on direct current is because these transceivers, amateur radio equipment, is designed to operate from a car or from a battery. Therefore, when you're in an emergency situation and you've lost power, if you have a battery, you then can power your equipment. And if you're using the equipment at home, you'll have a power supply, as I said earlier, that converts the alternating current to direct current. So how do you generate AC? Well, we know that moving a coil through a magnetic field will generate an excess of electrons and create a voltage and a current. So here we have a simple coil. We have a north and south side of the magnet. And in the first illustration I had, we have the magnet moving, and here we have the coil is going to move. We have two rings, one for one side of the coil and one for the other side of the coil, and they will then be where the power terminals come off of, as you can see in the illustration, for us to draw off the voltage and the current. Now that rod, that is the thing that's the coil is attached to, can be driven by wind, it can be driven by water, steam, a crank, whatever can make that motion for you will be able to generate electricity. So first we'll start off, as you see in the top left, with the coil perpendicular to the north and south poles of these magnets. And you can see basically that creates zero voltage. So as it's rotating into that perpendicular position, it will have a zero voltage at that location. As we continue to rotate it to 90 degrees, we'll see that it then comes to over that period of rotation, comes to a peak, of a positive peak at 90 degrees. As we continue to rotate it, it'll begin to drop through the 0 point again and begin moving towards a negative peak, as you can see on the right-hand side. So as we complete a rotation, we're going to have one cycle that's going to go from 0 to a positive peak, back to 0 to a negative trough or negative peak, and then back to 0 or 360 degrees, which is the same thing, to 0 again, completing one cycle. And we do this over and over again to produce the sine wave that's coming out of, for example, your AC outlet in your house. This is a very simplistic one-coil system, but it gives you the idea as you move the coil through the magnetic field, as you rotate it, you're going to produce a sine wave. Now, if we wanted to, we could create a DC in this very similar method, but we use a different ring structure. And again, this is a little bit of depth that's not in the book, but just so you know, there is a DC type of generator that has a slightly different ring structure called split slip rings. Say that 5 times fast, split slip rings. And that allows us to create pulsating DC. Now, if we add more coils at different angles on the slip ring, or different slip rings, and we add them together with different coils at different angles, we can then begin to add multiple pulsating sine waves, pulsating DC sine waves, to our output. So here we see the first one, just having one coil, then we've added a second coil, and then we've added a third coil, and you can see, if you look at it, it's beginning to show the average voltage is increasing. So the first top illustration, let's assume for a second the average voltage across all of that time, or at least the time of the first cycle, the first peak, 0 peak to 0, let's assume that's 50%. We add a second sine wave to that, and you can see they algebraically will sum, and we're going to get something higher than 50%. When we go to a third sine wave being added into, the average will then go up further to much higher than 50%, maybe 75 or 85% of what the potential peak could be over time. And so that's how we create approximation of DC. To put it a little bit further, we have multiple coils, and we're pulling off multiple sine waves, and when they're being added together, and then we can add additional components to the circuit like capacitors that will help bridge the gap. So by adding a capacitor circuit, which we'll learn about later what capacitors are, we are able to charge up that device from as the sine wave is going up, and as the sine wave starts to go down, it forces the component, the capacitor in this case, to discharge, and it discharges to sort of bridge to the next sine wave. And we do that enough times, we can begin to get an approximation of a DC signal output. And that little bit of ripple is actually considered a indicator of the quality of the conversion from AC to DC. Now again, this is not in your book, it's a little bit more detailed, but this gives you an idea of how we convert AC to DC through a DC generator, okay? Now, we could have AC coming in from the wall in your house, and you can see that on the left is an AC input, and we can put it through a device, which we'll learn a little bit about later, called a full or half-wave rectifier. This is a full-wave rectifier that we're seeing here in front of us in a symbolic form. And as the AC goes through, it produces that pulsating DC again. So we don't have any mechanical things moving. We're not generating it. We're taking what was generated from the line at your house, and we're using this device to convert it to pulsating DC, and then we use that filtering circuit, those capacitors again, to bridge that gap to create an approximation of DC. And so that's how we create DC, oftentimes from an AC signal, or when we're using a generator that's designed to put out DC. Now, batteries are a great source of DC. They are able to function for a certain period of time, and then, of course, they're depleted. So what you're seeing is different chemistries of batteries, and different chemistries of batteries have different performance characteristics. And you match the performance characteristics to the kind of work you want to do. More and more of the amateur radio community is moving from traditional lead acid batteries, which are the kind of batteries that are in your car, generally speaking, and moving to lithium ion batteries. And you can see from the left side that a lead acid battery at 13 volts begins to have a discharge curve that is fairly gentle and going down to 100% discharge, but it means that you're not staying at 13 volts for very long. You're constantly under load going down over time. As you can see with the red line, the lithium ion batteries, they try to maintain their voltage as long as they can until they reach a point where they can no longer maintain that load, and then they begin to discharge and deplete much faster. So the lithium ion batteries can operate at a fixed voltage level for a longer period of time than lead acid. The other thing that lithium ion can do is it can be recharged and charged many, many more times than lead acid, and they're also lighter. On the right, just if you want to compare the difference between an alkaline AA battery to a lithium AA battery. So these batteries are both designed to put out 1.5 volts. They're both the same physical size, but their chemistries are different, and you can see, again, the advantage of the lithium AA battery has a longer life at a specific voltage than the alkaline battery does. Again, different battery chemistries for different types of work. There are advantages to having a lead acid battery in your car that a lithium ion battery by itself in a conventional gasoline engine will not be as efficient at. But this is changing now as we have better and better chemistry in the lithium ion area, and some new chemistries coming up on the horizon that will eventually replace the lithium ion as well. So now that we know how AC and DC are generated, we now know that DC is direct current, it's direct voltage, it's instant on, and AC, alternating current, is a voltage and current that is changing over time, and it's generally symmetrical as we saw as a sine wave. Now let's talk about how you measure voltage, current, and resistance. So before we get into the details, let's look at water flow and see how we can use this as an analogy for what's going on with voltage, current, and resistance. So we're going to have water molecules represent electrons, and a quantity of water is a gallon, as you know. A quantity of electrons is called a coulomb. And if you, just for fun trivia, if you ever want to win a trivia contest in a bar sometime, a coulomb is 6.242 times 10 to the 18th electrons, 10 to the 18th electrons. Now flow current is measured by the quantity over time. We traditionally would say gallons per minute or liters per minute. With regards to electrons, we call it coulombs per second. So coulombs per second is our indicator of flow. Now, the unit of coulombs per second we call amperes, and we represent that by two symbols. One is A for amps, or amperes, and the other is I. We use the I only for a specific equation. Other than that, when we're reporting the coulombs per second or the current, we report it in amperes, and we do not report it in what's called I. I is just for one specific or two specific formulas. And water pressure, if you think about water being in a lake and the pressure exerts, or water being in a tank and the pressure it exerts, water pressure is like voltage, and we represent the voltage with the symbols E or V. In common use is V for voltage. In a specific formula, we use E. If we're using a book that's a little bit older, they'll use an E, and newer books they use a V. Because I was trained a long time ago, I still use the conventional E, which stands for electromotive force. So that's where E comes from. The original term for voltage was electromotive force, or electrodynamic force, or EMF, and that's where the E came from. Today, the modern usage is voltage. So when we use some equations later on, we're going to represent voltage with an E instead of a V. You could just as easily write it with a V, that's okay. I'm just using the convention that I was taught many years ago. And again, as I said, the E stands for electromotive force, and that's where that came from, was Mr. Ampere, who the amp is named after, basically coined that term for us to use many decades, well, about 100 or so years ago. So let's go back and remember that voltage is a difference of a potential between 2 points, for example, the battery and a zero reference or ground state, or a minus terminal. So if we look at this circuit on the right, there's some elements. We have a battery, that's our electron source. It has a positive terminal and a negative terminal. The negative terminal is where electrons will be emitted from. The positive terminal is where they will return to. And that device, that brown multicolored object above the battery, is called a resistor, and that represents the work that's being done by the circuit, and we call that a load. And that resistor is an electric component, and we'll talk about that a little later, but that completes the circuit. The minus we call ground in DC. In AC, we don't have a ground, we have what's called neutral. And so that's a bit different. Doesn't act like a ground like we do in DC, but for DC, the minus side of a battery is called ground. And a circuit, as you can see here, is a closed loop where energy flows from one side of the battery, the negative terminal, to the positive side. And so that becomes a closed loop. If there was not a closed loop, if we had a break in that line, the current would not flow through the circuit because it could not return to the positive side. We have to close that circuit in order to get current flow. In fact, that's exactly how a switch works. A switch basically breaks the circuit, and when you break the circuit, you cannot have any current flowing. And so that's what a switch's primary function is to do, is to open the circuit, to break the circuit, and prevent current from flowing. And when you close the switch or turn the switch on, it closes the circuit. It basically shorts to create a continuous flow through itself, so now the circuit can be operational, and the electrons can flow from one side to the other. And the rate of energy flow, as I've said before, is called current, and it's measured, as I said before, in coulombs per second or amperes. We don't actually say coulombs per second, we say amps or amperes. So as I said, voltage is a difference of potential. So if we take a voltmeter and we take its probes and we put it across the object we want to find out the voltage is, then we are in parallel with that object, and then we can see the difference of potential between the red or the positive probe and the black, the negative probe. Now this is a voltmeter in the lower left corner, but actually we don't really have voltmeters, we have multimeters. Every meter on the market today measures many different things: voltage, current, resistance, and even some measure transistors, some measure capacitors, some measure inductors. But all of them, the basic function of multimeter is always going to be to measure voltage, resistance, and current. So we set the dial for the right current for what we're going to measure, in this case DC volts, and we put it across the battery and we get 1.49 volts. And again, we measure voltage parallel to the device we're measuring. And if we're measuring AC voltage, we have to make sure we're on the AC voltage setting of a meter. And if we're, of course, on the DC measurement, we're on the DC side of the meter. And this is the same diagram basically we had in the previous slide, but now we're looking at it in schematic form. A schematic is like the blueprint for an electrical circuit. So we have a symbol for a battery, and we know the voltage of the battery because we've written it in. The symbol there stands for a battery, and we've assigned that battery to 24 volts. We have, in this case, we don't have one resistor. We have two resistors, or two loads in the circuit, and we have one that is at 250 M, and that's the symbol for ohms. You'll learn about ohms later. It's a measurement of resistance. And because it's M for mega, we know that that means 10 to the 6th power. So that's 250 times 10 to the 6th power. 250 mega ohms is 250 million ohms. And we have the one below it, the other resistor, is the same amount. And what we do is we want to find out the voltage across that resistor. We put the voltmeter in parallel to it, and we'll get a reading. In this case, I can tell you the reading is going to be 12 volts. And the reason is because these resistors are exactly the same, and therefore half the voltage will flow through one, and half the voltage will flow through the other. So the common units you need to know are things like microvolts, millivolts, volts, and kilovolts. Now, the thing that's going to be common here is micro, milli, and kilo, and mega. So micro is 10 to the minus 6. That's a decimal point followed by 6 zeros. Millivolts is 10 to the minus 3, which is 0.000, or if we have 1 millivolt, 0.001 millivolt, or 1 volt. We drop the millivolt, so if we actually say it that way. So we could say 1 millivolt, which is equal to 0.001 volts. we can have 1 microvolt, which is equal to 0.000001 volts. We could have, like in this case, 24 volts. And kilo means you're multiplying by 1,000. 10 to the third is 1,000. So if we had 2 kilovolts, it would be 2 times 1,000, which would be 2,000 volts. So these are the kind of things that units you're going to work in as we go through and look at the rest of the course. So now let's talk about measuring current. And as I mentioned before, when you measure current, we're going to have to break the circuit and put something that measures the current in the circuit to act as the item that's going to complete the circuit again. And then the current will flow all through the meter. And because the current will flow all through the meter, we will be able to get the total current of the circuit. So the amount of charge in coulombs, again, moving past a point in the circuit per second, is amps. We measure in series with the circuit, so we actually have to open the circuit, put the meter to bridge the opening in the circuit so that all the current goes through the meter. And the item being powered or doing the work is called the load. That in this case is an LED light bulb. And the load appears to the voltage source as a resistance to flow. So everything has some sort of innate resistance except for superconductors. So even a light bulb fully on has some level of resistance. And excuse me. Again, the way we measure with an ammeter is in series with the circuit. So you have to break the circuit, put the meter in to complete the circuit so the current flows through the circuit. And here we see what we just did with the meter again. We've got this meter. We've opened the circuit up so the meter probes can then have the voltage of the current going through the red part of the lead, the red lead, into the meter, and then the electrons flowing out of the black lead back to the battery in the circuit to complete it. And in the process of going through the meter is able to measure the current flow. Now, I only had one picture of a meter, so it's set for 20 volt scale DC. In reality, that was not what we would be setting it for. We would be setting for on the amperage scale, which you see the A on the right side in white. So I apologize, the picture doesn't match what we're doing, but that's the picture I had at the time, so make believe time. Okay, next we have a schematic representation of, just like our previous schematic, we have 2 resistances or 2 loads, and we want to find the total current of that circuit. So we break the circuit in some way to put the ammeter in, so the electrons flow through the ammeter, and then we can measure the current through the circuit. And we have things like microamps, which again is 10 to the minus 6 for micro, milliamp, 10 to the minus third for milli, and then amps. We don't generally deal with things like kiloamps unless you're in a power station where they're generating current for an entire community. So we generally deal with microamps, milliamps, and amps. And just a little bit of review, meter placement for measuring these different levels, voltage and ammeters. So in red we have a voltmeter. As you can remember, it's measuring in parallel to the device we're going to measure, and the ammeter is in series. And that's the left side, we have a series circuit. On the right side we have a parallel circuit. You can see all 3 loads are in parallel to each other. They have their own paths back to the battery, and therefore we can measure the total current in the circuit by breaking the circuit near the battery, and then we can see all the current moving through the circuit. Or if we want to see the current going through one node of this network, one load of this network, we just open up the circuit where that one load is and put the meter in, and we can measure the current through that node of the circuit, or for that load. So those are 2 ways we can measure current in this kind of parallel circuit. So I talked about this earlier. How do you measure AC volts? And it's difficult because when you look at this waveform, you say, okay, if I'm averaging the voltage across this waveform over time, what do I get? I get 0. Because as we go from, let's say, plus 1 volt, let's call it 1 volt peak, VPK is peak, on the positive side, to a negative 1 on the trough side, what do we get? Plus 1 plus minus 1 is 0. So if we were to sum this voltage, it would be 0 from a DC point of view. So our meter is not going to be able to function that way. It's going to see that even an AC meter is basically, excuse me, the AC side of a meter is basically doing a conversion to make it appear to itself as being DC. And so what do? We have agreed conventionally to use a method called root mean square. I won't go into details of how that method is worked out, what it actually means, but just to understand that we have all made a convention across the entire world that when we measured voltage, the DC equivalent for that voltage is going to be called, for AC, is going to be called VRMS, which stands for root mean square. So if I have a 1 volt peak signal, the root mean square, as you can see here, is 0.707 volts. So your meter, when you plug in your AC voltmeter into this circuit, it's going to read 0.707 volts. It will not read 1 volt peak because the meter doesn't read AC that way. It reads AC only by converting it to a equivalent DC. So you can see US house voltage is 100 volts RMS, or 100 volts root mean square. As I said before, it's 170 volts peak. And if you look at the full excursion from positive to negative, and you take the absolute value of the negative side. So if you remember, we take the absolute value of a negative number, it becomes positive. So the absolute value of minus 170 is a plus 170. So plus 170 is 340 volts peak to peak, and that is the span of US household voltage coming out of your receptacle. But if you put your meter on that, it's going to read 120 volts root mean square RMS. And so that's some things that you need to know about, is that there's something called root mean square. The positive excursion, at the maximum positive excursion of the sine wave, is called peak, voltage at peak. And the full span of the sine wave from the positive to the trough, with the trough being the absolute value taken of that value, is peak to peak. So how do you make these calculations? Is we go back to that circle method we talked about in the last session and also in the special video I made. We take the VRMS, we put it at the top, because you can see in the yellow box, it's on the left side of the equation, so it goes to the top section of the circle. And then we have V peak on the lower left, and we have 0.707 at the lower right. And now if we want to find out what VRMS is, we just multiply V peak times 0.707. If we need to find out what the peak voltage is, I cover V peak with my thumb, and I get the equation VRMS divided by 0.707. And if I want to know what V peak to peak is, all I have to do is double the peak voltage. So once I've calculated peak and I need to know peak to peak, you just double it, and then you'll get the full span of voltage. We're using the negative side to be the absolute value of the negative excursion. And so again, that's how we do that. So whenever we're using an AC voltmeter, we're actually measuring in volts RMS. And if we are asked a question about what's the peak, we now know how to get to that by using this circle method. And if we have the peak and we need to find out RMS, we have the circle method again to find that answer out in. But the thing to keep in mind again is that RMS is what we're going to call the DC equivalent voltage. When we make any calculations with AC, we're always going to basically use RMS for our calculations unless we're sizing components. And when we're sizing components, we have to make sure that they can withstand the peak voltages, not just the RMS voltage. Again, to convert from RMS to V peak, we use the circle method here, as you've learned before. So we've learned about the AC and DC electricity and how it's made. We've learned how to measure voltage and current. We'll learn how to measure resistance a little bit later. And now let's go in and talk about some of the components that we generally use in amateur radio. So the one we use most of the time, the one we've already introduced a bit, is resistors. And a resistor is like friction. It impedes the flow of electrons. And so here we have the battery, and battery is represented by a water tank with a certain level of water in it, which means it has a certain water pressure exerted by that level of water tank. And we have a pipe. We're going to call the rate of flow of that pipe as X. Now, if we have the same amount of water in the tank and we put a smaller pipe in, it makes sense that we're going to have more resistance to flow, and therefore we're going to have less flow, so the rate will be less than X. So the smaller and smaller the pipe we make, the more resistance there is to flow, and therefore the less flow that we'll have out of it. So as I said, most electrical items have an inherent or internal resistance, except for superconductors. There are special components called resistors that provide a fixed or variable amount of resistance. And a variable resistance is like having a valve in this water line that we can go from fully open to fully closed, so we can have any value in between. And as we change the size or the opening of the valve, we're essentially changing how big the pipe is, and so we can vary that, and that variation gives us a varying resistance. So a valve in a water pipe acts just like a variable resistor. So what is a resistor used for? Well, first to change voltage or currents in parts of a circuit. Certain parts of a circuit may need different types of voltages to operate properly. And so we use resistors to change the voltage levels through the circuit at different places. Now, what happens to the power or the voltage that we are resisting? Well, what happens is it becomes heat. And so resistors dissipate the energy that they are using as heat. Okay, and then also we can use resistors to limit the current used in a circuit by a component. So if a component has a specific amount of current it can handle, we don't want it to go over that amount of current. We use a resistor to limit how much flow there can be around that component to prevent it from becoming damaged. And we can use a resistor as a transducer. That is a thing that converts one energy into another type of energy. So in this case, we can create a transducer, a resistor, that convert changes in temperature to resistance, or changes in light to changes in resistance. And so if we put a voltage through this resistor that's sensitive to temperature, or a voltage through the resistor that's sensitive to light, then as one of these components changes, the temperature changes, the voltage will change. As the light changes, the voltage will change. And so we can then read what the temperature is or the intensity of light is by looking at the change in voltage. And the last is a way to convert electrical energy into heat. Think of this as your heating pad. So if you have a heating pad at home, or you have a heating element on an electric kettle, we have a very high resistance that's converting that electrical energy into heat. And we have here what's called a 50 ohm dummy load on the right. That is used on transceivers so that when you're testing them, you don't want to transmit, you therefore can put this at the back end of the transceiver where the antenna comes out, and then when you transmit, all the energy from your transceiver goes into this resistor, and the resistor then dissipates the energy as heat. And that's what those fins are on the dummy load. Inside that is a resistor. It gets very, very hot, so it has these fins to help it cool down, and that's what we use to dissipate energy when we're testing a transceiver. And the units of resistance, as I mentioned in one of the earlier examples, is ohms. Now, conductors have very low ohms. They just love letting electrons move through them. Conductors just have very little resistance, very low ohms for electrons to move through them. And insulators have very high ohms for electrons to move through them, so they don't move very well at all. In fact, in some cases, almost not at all. And so when you have an insulator, it basically is used to protect something that's going to be around a conductor. So we have insulated conductors, so you can touch a wire because it's insulated. In other words, if I put a red plastic coating around a bare wire, that acts as an insulator because the plastic coating does not conduct electricity very well. It's an insulator. So I can actually touch the wire. If that wasn't there, I could possibly hurt myself touching a conductor that has voltage going through it or current going through it. And semiconductors are a special class of solid-state devices. They are not like conductors or insulators, and they're in a special class all their own, and we'll talk about them very, very briefly later on. And as you can see, we have our circuit of the battery and the load or resistor, in this case, in the center. And then we have the schematic diagram. In this case, I've just changed the resistances from one to the other for 200 ohms to 500 ohms. So the symbol you see there, the omega symbol, we use to represent ohms. So 200 ohms on the middle one and 500 ohms on the far right. And again, as I said before, some resistors are built with materials that react to temperature or light. They either increase or decrease the number of ohms in response to those effects. Because you can build a resistor that responds to temperature either going higher in resistance as the temperature goes up, or even going lower in resistance as the temperature goes up. And the same is true for light. It just depends on what material you make out of, and then you go from there. And then if you want some trivia, it's not in the book. If you want to ever win a bet in a bar or something with a bunch of electronics students, the inverse resistance is conductance. It's measured in Siemens, and the symbol is G. And what kind of types of resistors are there? We have on the left linear resistors like fixed resistors and carbon composites and wire round and thick film, etc. We have variable resistors, which you can see have some sort of shaft in some way on there, and you actually rotate the shaft and it changes the resistance. And then we have rheostats, which you don't see very often, but they're not used at all in amateur radio, but there in things like light dimmers. And then you'll have trim pots, which are the same as potentiometers. Trimming pot stands for trimming potentiometer. It's the exact same as the variable resistor potentiometer. It's just in a very small package that's used to be mounted in a printed circuit board. The one on the top you'll find in many, many different AM and FM radios, because that is oftentimes your volume control. When you are turning the volume up or down on a radio, you're often turning a potentiometer. And then we have different types of nonlinear resistors, like I mentioned. The kind of resistor that will be sensitive to temperature, it's called a thermistor. One that's sensitive to light is an LDR. We have specialized ones called varistors, which are used oftentimes to help protect power supplies from voltage surges. And then we have resistors that are surface mount, which means they're very, very small little things. They're small little boxes like this. They're probably the size of about a lead pencil, the black part of the end of a lead pencil where you write with. They're very, very small, and modern electronics are often built with different types of surface mount components. We have about 4 different symbols here. You can see they all have the same base, which is kind of the stair-step mountain look symbol, which is a fixed resistor. If we add an arrow at the middle of the resistor, as you see the second one, that becomes a variable resistor. 2 arrows pointing at a diagonal means it's a light sensitive resistor, and kind of the thermistor with the knee that goes across it is a thermistor. The ones we generally use and see in amateur radio are the first 2. You'll also see, as we had in the diagram, some resistors have color bands around them. And these are carbon composite or carbon film resistors. And these bands all have meaning. You're not responsible to know the meaning of this or decode them for a test or anything, but just so you know, we have a color code. Black, brown, red, orange, yellow, green, blue, violet, gray, white stands for 0 to 9. And where the band is located tells us something about the resistance. So in this case on the left, on the far right, we have the orange, black, red, and gold on the brown carbon resistor. Orange stands for 3, so black stands for 0. So the first 2 are the bands are the first 2 digits of the resistor, in this case 30. The next one tells us how many zeros to put after the 30. So red is 2, which means it's times 100. So it's 30 times 100, or 30,000 ohms. And the silver is the tolerance, which means it's plus or minus 5%, because that's what the silver means. And that plus or minus 5% means that the value of that resistor is 30,000 ohms plus or minus 5%. If it's within the 5% tolerance, it's called a good resistor. If it was out of that, it would be out of tolerance, and we would then decide to choose for a circuit that needed 30,000 ohms. We would then use something different. And depending on how precise we want that component to be, we determines what value of tolerance we want. The higher the tolerance, the more expensive the part becomes. The other thing that's not shown here is that the diameter of this resistor indicates how much power it can handle. Remember, resistors dissipate energy as heat, and heat is watts, just like a 100-watt light bulb or a 15-watt light bulb. That's all heat. So the size of the resistor, that is the diameter of the resistor, tells you how much heat it can dissipate. There are resistors that dissipate 1/8 of an amp, 1/4 of an amp, 5 amps, 10 amps, etc. Because if you go beyond the amperage level of the resistor, or the wattage level of the resistor, excuse me, I said that wrong. Excuse me. Let me go back. I didn't mean amperage. The diameter tells you what the wattage of the resistor is. So there are 1/8 watt, 1/4 watt, 1/2 watt, 1 watt, and above resistors. And so you want to make sure that you size the circuit so that you do not exceed the watt capability, the power level of the resistor. And we'll go more into wattage later on in 2B. But just for this point of view to say, You don't want a resistor that has a wattage level that is less than what your total circuit could be, because it will burn out. And I will tell you, when they burn out, they produce a lot of smoke and they smell bad. Remember that dummy load? Well, remember, at a 100-watt transmitter, putting out a 100 watts into that dummy load means that that resistor has to be able to handle the heat of 100 watts. So that's the dummy load is probably about, in that one I know, is about 1.5 inches in diameter with all the fins. That makes it about 1.5 inches in diameter. Itself is smaller than what's in that package, but the fins allow it to extend and dissipate the heat, so it can be a little bit smaller than it would be if it didn't have the fins or heat sinks on it. So the diameter indicates the wattage. The bands indicate the value and tolerance of the resistance on a carbon composite or a carbon film resistor. Again, going a little deeper here than your book does. So we're going to look at some stuff now, and it's going to be schematics and it's going to be some equations, but I want you to keep in mind, don't panic. It's a lot easier than you think, and again, I'm going to tell you, I'm going to go a little bit deeper than the book just for your appreciation in the future. So if we want to sum the total resistance of a circuit, we have two basic circuits. We have a series circuit on the left, and we have a parallel circuit on the right. When we have a series circuit, all we have to do to find the total resistance of a circuit is add R1 to add R2. Or if we had 14 resistances or 14 loads, we'd add R1 all the way to 14 to get the total resistance, as long as they're in series. However, when we have resistances in parallel, we have to use a kind of funny formula. And we have two potential formulas. One formula is the general formula, and you can see that is total resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R3, all the way to what number, any number in the network. If we only had two resistors in the parallel network, we could use the formula below, which is R1 times R2 over R1 plus R2. If you did not want to remember the second formula, the first formula will work fine for two resistors in a parallel network. If you want to learn both, that's fine. Now, when you look at the first one with all these 1 over 1 overs, it looks really difficult at first to solve. It's actually a lot simpler than it looks, because we're going to use something called the inverse function on your calculator. So if you have a scientific calculator, you're going to have a 1 over x key. That's the inverse function. And what that key does is it does an automatic calculation for you. And the calculation is 1 divided by x. So if you didn't have a scientific calculator, you just have to go 1 divided by x. It's the same as that key. So what we're going to do is we're going to take we're going to put the R1 value in and hit the inverse key, or we're going to do 1 divided by R1, and we're going to write that number down that it comes down, because that's the inverse. And we're going to get the inverse of R2 and the inverse of R3, and then we'll just add them all together, and we'll get a number. And then we're going to take the inverse of that number, which is 1 divided by that final number, to get the actual total resistance of the circuit. So let's work through one of these. So don't panic, remember? This is a rather complex circuit for resistances or loads. And this could be a motors and lights and all sorts of things. Not very normal for us to do this kind of thing in amateur radio, but just to give you an appreciation. So how do you solve this? Well, we know that when we get to a series circuit, all we have to do is add the resistances up. So the first thing we want to do is convert all the parallel resistances into one equivalent resistance. That's the RT that we saw before, until we get down to a series circuit. So we would use, for the first two, R1, R2, and R4, R5, we could use the two resistance parallel circuit formula, as I show above them. And for the R7 through R10 network, since we have more than two resistances in parallel, we would use the RT equals 1 over R1 plus 1 over R2 plus 1 over R3, etc. formula to evaluate those. Again, you could use the lower formula to do the R1, R2, R4, R5 as well, but it's your choice. We just want to make sure that we evaluate R1 and R2 as one value, one equation, R4, R5 as the second equation, and R7 through R10 as the third equation. We can't lump them all together because they're in different parts of the circuit. And so once we've evaluated those resistance networks, we can then replace them with one new resistor. So RT from the formula on the left becomes the value of the resistor from calculating the network R1, R2. We'll call that RA. And then we'll calculate the value equivalency for R4 and R5, and that becomes RB. And the value equivalency for R7 is going to be R7 through R10. Sorry about the hyphen there. And so then once we have those all done, you'll notice we have a series circuit. There's no parallels left. And now we just add up RA plus R3 plus RB plus R6 plus RC plus R11 to get the total resistance of the circuit. Now again, just giving you a sense of how to solve this problem. You're not going to be required to solve this kind of problem on your test, and most amateur radio operators don't have to deal with problems like this in their career. But it's just, again, a little appreciation of how these problems are solved. But you will solve problems like this. So let's do a little practice. We have a 4.5 kilo ohm resistor, a 250 ohm resistor, and a 1.2 kilo ohm resistor. Notice we have K's on two of them and no K on the other. What's K mean? It means you multiply by 1,000. So we have 4.5 times 1,000 equals 4,500 ohms, 250 ohms. And here we have the K again, so we multiply by 1,000. We have 1,200 ohms. And what we want to find out is what's the total value of resistance in the circuit. And so we calculate that all up, and we get 4,500 plus 250 plus 1,200, which equals 5,950 ohms. So if I wanted to replace all three of these resistors in this circuit, I just have to use a 5,950 ohm resistor. Now, you're not going to do that necessarily because these all represent potentially something you need to have happen, but just so you know that the total resistance of the circuit is 5,950 ohms, and if you had to calculate current, that's the value you would use to calculate the total current in the circuit, and we'll learn about how to do that a little bit later. Now, if you have a parallel network, what we're going to do is that inversing again. So we have 200 ohms, 250 ohms, and 650 ohms. And you can see we're going to take the inverse of 1 over 200. That's 1 divided by 200, plus 1 divided by 250, plus 1 divided by 650, which gives us 0.005 plus 0.004 plus 0.0015. We're going to add those lower numbers together. We're going to get 1 over 0.105, which is 1 divided by 0.105. That'll give us 95 ohms. So the equivalent resistance of those three together is 95 ohms. You can replace all three of those with a 95 ohm resistor, which will then be the series equivalent resistance. So one thing to notice here is that you notice when we look at these three resistors, the 200, 250, and 650, that the value we calculate is less than the lowest value in the network. And that is one of the ways you know you're doing it correctly. If you were to end up with something like 225 ohms, you did it wrong. Why? Because you cannot get, excuse me, in this system, a resistance higher than the lowest resistance in the parallel network. So that tells you when you got it right, a little cross-check. And I think this is the same problem again, so I apologize. I'll have to take this slide out. So here we have a little bit more practice. Again, this is a little bit more complicated than you have in your book, but you can see right away, we want to always, when we want to find out what the total resistance is, we have to get everything down to a series circuit, and we see two parallel resistors, so we have to solve those first. So if you want to play at home, you can stop the tape and do the calculation, or you can follow what we're going to do now. So the first thing is we're going to solve the parallels first. And because there's only two in the network, you can use the special formula R1 times R2 over R1 plus R2. And we end up with 181 ohms. We know that's probably right because it's less than 250 ohms. Remember, in a parallel network, the total calculation for that network is going to be less than the lowest value of resistor in the network. And now if we replace that network with a 181 ohm resistor, we have a series circuit, and then we just have to add 4,500 ohms to 181 ohms to 1,200 ohms and give us the total resistance of 5,881 ohms. And that's how you solve that problem. So I said you want to be comfortable with different levels of scientific notation equivalencies. And so do not worry about what's on the right. That's for entertainment purposes. I love the 10 to the 24th power. It's called a iota. Iota, I think that's the way it's saying it. And so, but the ones that we use in electronics are pico, which is, as you can see, is 10 to the minus 12. We can count off the zeros from the right side of the decimal place. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. In the 12th place, I've just made it a 1, so that's 1 pico is what we have written here. So the 12th place. If we had 10 picos, it would be 0.0000000000010, which would then be 10 picos. Okay. Nano is 10 to the minus ninth. Micro is 10 to the minus 6, so you can count off 6 zeros, 0.00000, and the 6th one I made a 1 for 1 micro. Milli, we have 1 milli here, 0.001, which stands for 10 to the minus 3. Kilo is 10 to the third power, or 1,000. Mega is 10 to the sixth power, or 1 million. So those are the things you need to know. Those are the ones you need to know. So we're going to stop here, this video, and we're going to start with the next one, session 2B, and we're going to cover the rest of the components and some of the formulas that we'll use for calculations. So stay tuned.